All right, so before we continue on, I want to point out a couple useful sequences that's important to recognize. Of course, first two are just our odd numbers. There's two different ways we can represent those. Uh, First is as 2k plus 1, as k goes from 0 to infinity. And that's one way to do it. And then you also see them as 2k minus 1, where k starts at 1 and goes to infinity, produces the same sequence. This is basically just a shift in the sequence, right? From k equals 0 to k equals 1, we're just shifting the sequence by 1. But of course, that affects this piece here. Right? When we replace k equals 0 with k equals 1, right, we have to make that adjustment. You can see that we get 2k minus 1. And of course, the other one we saw with the cosine, and that is the even numbers, 2k. Okay, so we'll see these things coming up, and we kind of got to keep our eyes open for them, because these kind of patterns and how we represent them are going to be important as we're looking at further series. So on the last example, we found the Taylor series for the cosine. We found the Taylor series for the cosine centered at 0, and we saw that it converged actually for all real numbers. Well, using our knowledge from before, we could build, just like we did the cosine, we could build a Maclaurin series for sine using the derivatives of the sine function and looking at our coefficients. Or we could use the cosine function and take its derivative to build up the new sine sine series. So that's actually what we're going to do. We're going to use the cosine series that we found, and we're now going to construct the sine series. Okay? All right. So let's do that. So we take the derivative of cosine. We know that that is going to be minus sine. Right? Derivative of cosine is minus sine. That means that the sine function would be the negative of the derivative of the cosine. And then we apply the derivative of the cosine to our series. What was the cosine? Well, we had a minus 1 to the k. That's just the number, so that's just going to stay there. And then we're going to do the derivative of this thing, each polynomial term. Well, the exponent's x to the 2k. So remember, to do the derivative, we would multiply by that exponent. So that's going to be 2k x to the 2k minus 1. And that's all over 2k factorial, but 2k factorial can be written as 2k times 2k minus 1 factorial. And so the 2k's will cancel out. Now you might notice I didn't bother writing my indexes here this time. K equals 0 to infinity. And the reason is if we go back to the cosine, there is one number in the cosine polynomial when it's expanded out, to which this formula of powers that we're doing the derivative of doesn't work for, and that's 0. That's 0. So the 0 term's actually going to be disappearing. The 0 term's actually going to be disappearing. The 0 term is actually going to be disappearing. Okay, so what's this look like here? This will now be the series. When I bring that negative through, we'll actually make it be the series minus 1 to the k plus 1, right, because we're bringing the negative from the outside in. And we're going to have an x to the 2k minus 1 over 2k minus 1 factorial. And now the original series, again for cosine, is going to lose that first term. Right? This formula doesn't work until we ignore the first term, which was a 1. Derivative of 1 is 0. So that's going to be gone. So this is actually going to be starting from 1 and moving on to infinity. What's that going to look like? Well, first term, you plug in a 1. Minus 1 to the 1 plus 1 would be minus 1 to the second. Plug in 1 here. 2 times 1 minus 1 will be 1, and that's over 1 factorial. So that would just be x. Next term would be 2. 2 plus 1 is 3, so that's going to be minus. 2 times 2 minus 1. 4 minus 1 would be 3 over 3 factorial. So that's going to be x cubed over 3 factorial. And then skip x equals 2. It's going to be, sorry, x equals 3 now. We would be 3 plus 1 is 4, so it would be plus. And again, 2 times 3 is 6, minus 1 would be 5. So x to the 5th over 5 factorial. And we continue, minus x to the 7th over 7 factorial. Plus, and then so on. Plus, and then so on. Now that series starts at 1. We can easily adjust this to make it go 0 if we wanted this first one to be our 0 term. Right? Coefficients are the odd numbers. So again, we're doing odd numbers this way, but we can easily reset everything so the odd numbers start here. And if I'm doing that starting with 0, then I'll have to adjust this coefficient as well. So we can write this down as the series as k goes from 0 to infinity. So I want the first term to be positive, so I'm going to make it minus 1 to the k now. And then I replace my odd numbers. So that'll be x to the 2k plus 1 over 2k plus 1 factorial. Okay. So we're just shifting the variables back 1. Everything's shifting back 1. Okay. So starting at 0 now, I need the 2k plus 1 to make that a 1. And of course, now the exponent, I need the 0 term to be positive, so it needs to be minus 1 to the k. And then the 1 term, which will now give me 3, will have a negative sign still. The x equals 2 term, k equals 2 term, which will now lead to an x to the 5th, will now be positive, and so on and so on. The pattern continues out. Okay. So now we've been able to build the sine series from the cosine series. And since we know that the cosine series converges for all real numbers, then we also know that the sine series also converges, because the sine series we generated was developed by doing the derivative of a convergent series. So since the original series converged for all real numbers, the derivative also will converge for all real numbers. Of course, we could have also opted, if we had wanted to, instead of taking the derivative of cosine, we could have integrated cosine and gotten a result for sine. You may want to consider doing that just to see. It should lead you to the same series. It should lead you to the same series.